Welcome to the continuing video podcast series here at Ontario High School. We are looking at combustion analysis stoichiometry today, and we're doing this along with the Unit 9 stoichiometry unit here at the high school, where we look at gas and solution stoichiometry, and now we're going to focus on combustion analysis. Welcome. Let's look at some characteristics of combustion analysis. What will happen is that we'll take a sample and burn it in the presence of excess oxygen. The substances usually being studied include carbon and hydrogen, though not always, but most of the time. All of the carbon in the sample is converted to carbon dioxide. All of the hydrogen in the sample is converted to water. This can be very important for us to understand. If oxygen is part of the original compound, its mass will end up being contained in the oxides. Its original mass in the compound has to be found by subtraction. If nitrogen is in the compound, its percent in the compound is usually found through a second experiment, and the nitrogen in that will usually be found as either N2 elemental nitrogen, or as nitrogen in ammonia, or as an oxide, nitrogen dioxide, for example. It is critical that the original mass of the compound before burning is noted, though you will not always be given that, and there are ways to work around that. When we get there with sample problems, you'll see how that works. Here's a rough diagram of a basic setup of a combustion analysis reaction. You can see oxygen is flowing through the area where the compound to be analyzed is. It's heated so that combustion takes place. The gases from the combustion are then forced through, in this case they show a U-tube that will absorb water, and then through a U-tube that will absorb carbon dioxide. And then the unused oxygen gas just leaves out, in this case, the right side of this apparatus. And that's basically how this is done. And it's, again, just a look at a simple setup for this. If you ever get to use combustion analysis, it will probably be at the university level, and your apparatus will look a little bit more complex. But this gives you a basic idea of what it's about. Let's just take a look at the basic steps. We're going to use mass ratios to determine the amounts of carbon and hydrogen present in the original compound. For example, when you do the molar mass of carbon dioxide, you know that there's 12 grams of carbon and 32 grams of oxygen, which make a total mass of 44 grams per mole of carbon dioxide. So the carbon in the carbon dioxide can be described as being present in a 12 gram over 44 gram ratio, or a 12 to 44 ratio. Hydrogen is always present in water in a 2 to 18 ratio, 2 grams of hydrogen for every 18 grams of water in terms of 1 mole of water. After we determine the mass of the carbon and hydrogen using these mass ratios, we'll next convert the grams of each element to moles. And once we have them in moles, we can determine the empirical formula by comparing the mole ratios. Once we have the mole ratios, we can write the empirical formula for the substance and then compare the empirical formula mass to the molar mass. The molar mass is usually provided in the problem, and we'll determine the molecular formula if we're given a molar mass that does not match the empirical formula mass. And just as a way of review, months and months ago we covered how to determine empirical formulas. We had a little poem that we memorized. So here it is. Percent to mass, mass to mole, divide by small, multiply to whole. Now the good news with combustion analysis, you're almost always given the mass of the carbon dioxide in the water. In fact, you are given the mass of the carbon dioxide in water. For that reason, once you determine the mass of the carbon and hydrogen, you don't have to worry about the percent step here. It would just be mass to mole, divide by small, multiply to whole. Well, let's apply these principles to a sample problem. Here we have a 1.50 gram sample of a hydrocarbon, And a hydrocarbon is a compound that contains only carbon and hydrogen. So whenever you see a problem that says a hydrocarbon is burned, it's just carbon and hydrogen. No other elements are involved in the compound. It undergoes complete combustion to produce 4.40 grams of CO2 and 2.70 grams of H2O. Determine the empirical formula of the compound. So our first step is to use the mass ratios to find the grams of carbon and hydrogen. So our grams of carbon is equal to the mass of carbon dioxide, 4.40 grams of carbon dioxide, times the mass ratio of carbon in carbon dioxide, which is 12 grams of carbon over 44 grams of carbon dioxide. This calculation will provide us with the information that there are 1.20 grams of carbon. Grams of hydrogen, done the same way, 2.70 grams of water times the ratio of 2 grams of hydrogen for every 18 grams of water gives us 0.300 grams of hydrogen. Now that we have the grams, or masses of carbon and hydrogen, we can convert them to moles. So we'll take our 1.20 grams of carbon and multiply it times the equality, or our conversion factor, that has 1 mole of carbon on top, the unit we're going to, over 12 grams of carbon on the bottom, which is the mass of carbon in 1 mole. That you get off your periodic table. When we do that, we find that we have 0.100 moles of carbon. Hydrogen, we take our 0.300 grams of hydrogen times that equality or conversion factor of 1 mole of hydrogen over 1 gram of hydrogen, so we have 0.300 moles of hydrogen. Next, want to find the mole ratio by dividing all the mole quantities by the smallest. So for our carbon, we take its 0.100 moles and divide it by the smallest quantity, which is the moles of carbon, 0.100 moles. So we have 1 carbon. For hydrogen, we take our 0.300 moles divided by the smallest number of moles, which was 0.100 moles. So we get 3 hydrogens. So our mole ratio for carbon to hydrogen is 1 to 3. And because the mole ratios are whole numbers, we don't have to multiply to a whole. We can go ahead and write the empirical formula, which is CH3. With our next sample problem, we want to increase the complexity a little bit. And the way that we'll do that is we'll determine not only an empirical formula, but also the molecular formula for the compound. So here we have a 0.250 gram sample of a hydrocarbon that undergoes complete combustion to produce 0.845 grams of carbon dioxide and 0.173 grams of water. The molar mass, and you'll also see this as molecular mass, molecular weight, or gram formula mass, is 78 grams per mole. Determine the empirical formula and then the molecular formula for the compound. What I'd like you to do is pause the podcast at this point and try and work this problem through, get as far as you can, and then resume the podcast and we'll check your answers and see how you did. Welcome back. Let's see how you did. For our grams of carbon, we take the mass of carbon dioxide, 0.845 grams, multiply it by our mass ratio of 12 grams of carbon for every 44 grams of carbon dioxide, and we get 0.230 grams of carbon. Our grams of hydrogen is 0.173 grams of water times the mass ratio of hydrogen to water, 2 grams of hydrogen over 18 grams of water, and we get 0.0192 grams of hydrogen. Now that we have our grams of carbon and hydrogen, we're going to convert to moles. So 0.230 grams of carbon times 1 mole of carbon over 12 grams of carbon gives us 0.0192 moles of carbon. 0.0192 grams of hydrogen times 1 mole of hydrogen over 1 gram of hydrogen gives us 0.0192 moles of hydrogen. We next want to find our mole ratio by dividing all the mole quantities by the smallest. You're right now thinking they're the same number of moles, they're equal. Why show this? And the reason that I show it is it demonstrates the process by which I got to the right answer. So for my carbon, I take my 0.0192 moles and divide it by the smallest, which is 0.0192 moles, and get 1 mole of carbon For hydrogen, the mole ratio would be 0.0192 moles over 0.0192 moles, which gives me 1 mole of hydrogen. Since the mole ratios are whole numbers, I can write the empirical formula, which will be CH. I now have the empirical formula. It is CH. I need to determine the empirical formula mass for CH. So this would be 12 grams of carbon plus 1 gram of hydrogen would give us 13 grams per mole of CH, the empirical formula. And then I'm going to divide the molar mass. This is represented normally by an uppercase M or capital M, by the empirical formula mass, which we're going to represent by an EFM. So our molar mass divided by our empirical formula mass, that ratio, 78 grams per mole, divided by 13 grams per mole, gives us a value of 6. And that 6 is the ratio of the molar mass to the empirical formula mass. And we're going to do something very important with this ratio. When the molar mass of the compound and the empirical formula mass are not the same, what we do is we'll multiply the subscripts in the empirical formula by the ratio of the molar mass to the empirical formula mass to determine the molecular formula. Now in the case of CH, we don't have written subscripts because whenever the subscript is 1, it's implied to be there by its lack of presence. So when we multiply 6 times the subscripts of C and H, we get C6H6. This compound actually is one called benzene, and it's a very important compound in organic chemistry. So how'd you do? Well, we've come to the end of part 1 of the video podcast series that addresses combustion analysis, and stay tuned for part 2, very important, more complex problems that we'll address in that. I want to leave you with a quote from the great British statesman Edward F. Halifax: "True merit, like a river, the deeper it is, the less noise it makes." Think about that one. Very interesting. I wish you well.